Chapter-17. We're going to first today study the chemical reactions that we studied in early chapters that produce aldehyde and ketones. So the first is ozonolysis of alkenes. We study in chapter 6 and section 12. So the generic equation is like this. I get the wrong version. I'll use the one that has a blank. Alright, so there is many reagents that can produce the aldehyde and ketones. So the one we will try to talk about is in chapter 6, when you have the double bond, and you can take O3 ozone and cutting the double bond produce either aldehyde or ketone depending on the substitution on the double bond. Okay, so the general equation, you have a double bond and ozone, and then you follow up by zinc. So that will stop the oxidation furthermore, so you will stop at the aldehyde or ketone. So the example here is, I give you this alkane, so you have a double bond here, and what happens is the ozone is going to cut in this double bond and produce on the left side, you will produce the ketones. So let's see, first step, we're adding the ozone O3. Second step, and you adding water and zinc. So what we produce from the left side of the double bond, we produce this acetone, ketone. Then this carbon on the right side, so initially it has a structure like this. Now this will produce aldehyde. Then quickly review also those review. We can also hydration of alkyne, which is a triple bond, and that's the first chapter we studied, chapter 9. So in this reaction, initially you will produce a enamine, and then the enamine will quickly tautomerize to the ketone or the aldehyde. Okay, so here we have alkyne, 1 octane, and you will just take H2O with catalyst like H2SO4 and also HgSO4. And let me just also give you the enol intermediate. So you will produce the enol intermediate, and then the enol intermediate very quickly tautomerize. And this is the enol intermediate. It will tautomerize into our final ketone. If you start with alkyne, and the similar material like triple bond. You can also use the hydroboration and oxidation. You pretty much will get the similar product as you just simply take the water and acid and the mercury sulfate. But for those terminal alkyne, for the terminal triple bond, and you will produce a different product. Or for in general, for those unsymmetrical, just unsymmetrical triple bond, that means you have the terminal. And well, in the intermediate, you will also see those difference when you do the hydrations or hydroborations, oxidation. Usually, you will not use this method to try to produce ketones because you will produce a mixture. You can either put the inner on the left side carbon or on the right side carbon, so you will have different ketones. And your ketone location will be different. So let's say this hydroboration oxidation is apparently compared with those terminal alkynes. And if you use hydration, simply hydration, and you will produce the methyl ketones. If you do a hydroboration oxidation, and you will produce aldehyde. So that's our first approach. It's similar to what we did. My tablet running no problem. So what we try to say is when we have the terminal alkyne, terminal triple bond, and we are going to compare. One way is you produce methyl ketones by simply use the hydration. Hydration use the catalyst and acid catalyst. The other one is use the hydroboration and oxidation. Okay, so when my computer tries to start up, and I will just write something here. It's like this. So when you have a terminal triple bond, as you have R and C, triple bond C and H, you have two approaches to change the triple bond into aldehyde or ketones. One approach is just simply use H2O. And then some of the sulfuric acid and HeSO4. H2O and H2SO4, then mercury sulfate. And what you produce is a methyl ketone. So R, C, and C3, like that. If you use the hydroboration oxidation, and you will use B2H6, your first step. Your second step, use H2O2 and some of those base, and you will produce aldehyde. So you will produce CH3 and CH2, and then C carbon like that. So this is the two ways to convert the triple bond into aldehyde and ketones. Now let's see some some of those examples. Let's see some examples. I'll give some of those examples. One example is like this. Let's see, we have I want to compare. I think the example I put on the next note is I want to compare the hydroboration oxidation of double bond with triple bond. Okay? And here I compare the triple bond a different way to convert into aldehyde and ketones. And I also can compare the triple bond with double bond, the hydroboration oxidation. Now let's see, if I take a triple bond, I write this different than in the next notes. So if you do the B2H6 first step, second step you do H2 and O2, and this will change into the aldehydes. So we have 1, 2, 3, 4, 5 carbons, and your aldehyde probably add an ion, like that. And if you do a different approach, if you use H2O and H2SO4 plus the mercury 2 sulfate, and you will produce the ketones. Now we also can compare triple bond with double bond, and compare this two approach. You remember, like in the Chapter-17, you can either also do like the hydroboration oxidation and also do the simple hydration to the double bond. So if there was like also 5 carbon chain but with a double bond, and if I do a hydration, simple hydration, and you will produce bicarbonate product. If I do a hydroboration, now then you see I can get my computer back. Okay. Now I can use this, finish this crop, and I will put the diamond note. Okay. So what I plan to write for the alkene, 5 carbon double bond. Okay. So double bond as an ion. Okay. And you can do either H2O and with some of those catalysts, hydration of a double bond, and you produce the carbon product. Well, if you do the hydroboration oxidation, pH3, and then you oxidize it in some of those base solutions. And this product is anti or non And to the triple bond, you will produce the ketone or aldehyde. To the double bond, you will produce the alcohol. For both of these triple bond or double bond, you will have like the stereochemistry. So where you put the double bond, where you put the carbonyl, or where you put the hydroxyl. Right, now let's go back to the lecture notes. Chapter 17. Excuse me for my computer's problem. So in the lecture notes, you will see like a few more examples. Now the example is, we will talk about the triple bond. If you have this alkyne, this is terminal alkyne. If you first add the BH3, and then you use on the base, and then H2 and O2. For the same alkyne, let's emphasize the difference again. Okay. For the same alkyne, if I use H2O and then H2SO4 and HgSO4, what you produce, it will be this methyl ketone. All those are review. Next method of prepare aldehyde and ketones is the Friedel-Crepes acetylation of aromatic compound. The general reaction is you have some of those bendings, maybe cyclic bending, or maybe some of those substituted bending. If the bending is substituted, be careful. If you have some of those very deactivated group like nitro, or you have that aniline, some of those nitrogen on it, that will be difficult to have this reaction, to have the Friedel-Crepes acetylation or alkylation. Now, in the example, in the two examples here, and we have substituted bending, but right now the substitution on the bending is sort of the activator. So on the last exam, I see a few people still have difficulty identify the substitution on the bending is the activator or deactivator. general, those activator has the structure, have those structure like N, have like long pairs, and then you have the like the bending ring, or you have the bending ring and O with long pairs like that, and also those LQ. So those are activators. Activator in general has those kind of structure. So that means they have an atom bonding to the bending ring. Then your atom bonding to the bending ring have long pairs. Right. So then these two molecules, they both have those substituting on it, and they are both activators. For all those activators, they are also activators is also the para also directed. So not only the activator is also para-director, some of those deactivators. Okay? So few deactivators, and they are also also directors. A very common deactivators like halogens and some of those halo metals. They are also deactivator, but they are like also the para also directors. So try to memorize those patterns. Here you have this substitution on it. So when you use this 2-chloroether, and the Friedel-Crafts acetylation can still happen. You still need the catalyst, the AlCl3. These are our catalysts for the Friedel-Crafts reagents. You can use ethyl chloride to the acetylation, or you can use anhydride. And the anhydride can also supply the ethyl group for your acetylation. The second example, we use anhydride. AlCl3. So our aromatic compound in the second example is anisole. Anisole has methoxide, on the bending ring. So they are also para-directed. And I will just write the products, that metal products. So even though possible, you can put this ethyl group in the also position, but you did not see that having too much to a larger percentage. So this, from the literature, this is 90 to 94%. You did not see that that also products. So this is para products. Right? So this methoxide on it is also para-directed, but we only see this para product. The reason is those steric hindrance. The similar for the one on the top. The one on the top, so it's 85%. steric hindrance. On the last exam, I saw some people have difficulty to identify the oxidation agent and the reducing agent. Okay? So you first of all, if you want to change alcohol into aldehyde or ketones, you need to use the oxidizing agent. Okay? Reducing agents are those agents will supply you the H. Adding H on a compound that will reduce the compound. The oxidizing agent are those agents that has oxygen in it. If you are adding oxygen on your compound, so therefore your compound will oxidize. We have quite a few oxidizing agents in these few chapters. So most of them is chromic based. The chromic base depend on like the solvent. If the chromic based oxidizing agent is in those aqueous solutions, and their oxidizing power is stronger, so you will oxidize your primary alcohol all the way to the acetic acid. To the carbonic acid. So that if you use those chromic-based oxidizing agents and put them in those organic anhydrous environment, and their power is very less, and they will not oxidize your primary alcohols all the way to carbonic acid. They will stop in the aldehyde step. And two common examples of chromic-based oxidizing agents in the anhydrous environment is the PDC, the pyridinium dichromate, or the pyridinium chlorochromate, or PCC. So we can just simply memorize we have a chromic-based oxidizing agent, and if you see those H2CrO4 or something like those in water or in like sulfuric acid, they are stronger. And if I give you PCC and PDC, which means they are a little weaker. Okay. Another way is the so-called swarm oxidation method. Which was who is a chemist in Temple University. He discovered this oxidizing method by taking DMSO. So here, DMSO in the presence of oxylyl chloride. Oxylyl chloride is a carbon oxalic acid. You know what is oxalic acid? So this is oxylyl chloride. And then followed by trimethylamine. So sometime in the homework you will see these combinations, DMSO, and then this oxylyl chloride, and then see like trimethylamine. What that will do to your alcohol, it will change your primary alcohol into aldehyde, and it will oxidize your secondary alcohol into ketones. Let's see one example. See if you can identify if I have this one decanol. So this alcohol is primary alcohol. Let's see what this will produce. This is primary alcohol, right? Has have 10 carbon, and you use PDC your solvent you can see is methylene chloride, C2Cl2. It's not water. So reducing power in the liver like weaker. Now I draw this 10 carbon chain. What do you think it will be at the end? And we will have a carbonyl, and I will see whether we have a simply H or OH. If we have H here, we have the aldehyde. If we have OH here, we have the carboxylic acid. So for these oxidizing agents, what do we produce? Yeah. So it will stop in the aldehyde step. For this example, this 1-phenol, 1-pentanol, this is let's see the secondary alcohol. But for secondary alcohol, let's see, we also like to try one way. We see we are going to use what we used before. Let's see, PDC. PDC in the methylene chloride. C2 and Cl2. What do you think will produce this time? Ketone. So no matter what you use, as long as you can oxidize this alcohol, it becomes ketone. Very good. So ketone will be right here. What about if you use, let's say, chromic-based oxidizing agent, but in like aqueous environment? Let's see, I might simply write CrO3, okay? And then the solvent is acetic acid. Acetic acid. Let's see, this arrow continue, okay? And in water. So what this will produce? We still have the secondary alcohol, but this time we still use the chromic base. We have the CrO3. Now we use the solvent like the acetic acid and H2O. What will produce this time? Will you produce an acid, or you will produce a ketone? It still produces ketone. So you can produce an acid here, but you will not start with this. You will not start with alcohol. What we study in Chapter 12, right? In Chapter 12, and we have those kind of bending, substituted bending. If you have those structures, simply like that, right? And then you use those like the H2Cl4, which is same as CrO3 in water or in acid, and then we'll change into what? Then we're changing into our benzoic acid. So you cutting all the other carbon off, and we have one carbon, and that carbon have like carbonyl and then OH. So this is benzoic acid. Right. Now for this reaction, this is what I mean is I should move out like this. Okay, what's the word with the product? Okay, so this what I said. You need to memorize this type of oxidizing process. They call the swarm. It's the swarm oxidation agent, reagent. Right? So what you're starting with, yeah, where did I mess up my lecture notes? So we produce this. So I try to move the track. So this question is what reagent shall we use? So this is strong oxidation, oxidize the alcohol into aldehyde. Now let's identify what shall be our reagent. What kind of reaction shall we have? I think that's kind of easy, right? Alright, so that's our reaction. Okay. So these are our reaction. And you have this method here. And this was our initial OH. Okay, so if we know we can oxidize alcohol into ketone or aldehyde, and this also gives us a very nice way to a very intermediate and nice way to change carboxylic acid into aldehyde and ketone. You think about the carboxylic acid have a little higher oxidation state on the carbon. You probably think about you can reduce like the carboxylic acid into aldehyde or ketones, but usually it's difficult. So what you want to do, if you want to change the acid into aldehyde and ketones, you're not simply using a reducing agent. You are using a reducing agent that always reduce the carbonic acid into alcohol, then reoxidize it into aldehyde and ketones. Okay? So usually it's difficult to control if you're reducing directly into ketones from the acid. But you are reducing it all the way to the alcohol and then reoxidize. So convert acid into aldehyde and ketone, two steps. You first reduce it all the way to alcohol. And you convert these three types of compounds. So this acid, carboxylic acid, and alcohol, and a ketone. And you have this carbon that has those carbonyl or hydroxyl on it according to the oxidation state. So this acid, the carbon on the acid have the highest oxidation state. And alcohol have the lowest. Aldehyde and ketone is in the middle. Right, now let's see some of the examples, and you have to go all the way like two-way. If you want to change this benzoic acid, let's see the structure for the benzoic acid. Alright, so this is our benzoic acid. You want to change the benzoic acid into into benzaldehyde, you don't have a good reducing agent to reduce that into this one step. You cannot. What you do, you first use some of those reducing agent. Okay? Reduce this into alcohol. And this is our benzyl alcohol. Not too many reducing agents to reduce the carboxyl acid either. Okay? The one most frequently used one is lithium aluminum hydride. And that guy has very, very strong basic H. So therefore, when you use it, you cannot use it with any protic solvent like water, alcohol. If you use it with alcohol or water, water and alcohol will totally destroy your lithium aluminum hydride. And you have to use it in some of those aprotic solvent, like diethyl ether, methylene chloride. Once your reducing process is finished, then you can use water and work up. So now you can think about agent that will oxidize your alcohol. Even though this we call a benzyl alcohol, but this is still a primary alcohol. Right? It's possible you can change a primary alcohol into an aldehyde. You can obviously always change this back into your carboxylic acid. So what the oxidizing agent will we use to oxidize this alcohol into our kind of intermediate oxidation state? I think so far we have three choices. We can use what you see it in, what we can use?
PCC.
We can use PCC or what? PCC and or that has a very quite a few reagents. What is those one? Now here you can see you can also change aldehyde into a ketone by using some of those Grignard. But for those processes, you are getting more carbons. So the general reaction is that you take aldehyde, for example, aldehyde and Ylides, and you add in some of those Grignard, and then you work up. You get the alcohol. Right? So this alcohol will have more carbon compared with your initial aldehyde. Right? And then you can oxidize your alcohol into ketone. Okay, now here in this example, we see we started with this propanol, aldehyde with 3 carbon. So how can we prepare There's 3 heptanone. This is a ketone with 7 carbons. According to this procedure here, right, you are thinking about 2 steps. You start with reagent, and have like a 3 carbon, which is aldehyde, and you want to get a ketone, have a 7 carbon, and you need to add in more carbons. And we know a very good way to add in more carbon is using those organo lithium or some of those other organic compounds, maybe Grignard reagent. And then what we start in chapter 14, right? All the Grignard. So let's just write out those procedures as we listed out on the top. So if you want to change aldehyde into a ketone with more carbon, you first of all do a Grignard. Right? So Grignard reaction will have 2 steps. Like what we see on the exam. When you use Grignard, you cannot use those protic acid and protic solvent. The protic solvent means you have those proton in the available very, very easily. If you have the proton available, the proton will add on to your Grignard R and change your Grignard into hydrocarbon. You are lost in your Grignard. So always 2 steps. And now this time, you want to add in 4 more carbons. So therefore your Grignard should have 4 carbons. Now that is 4 carbon, then just write Mg here. So then in this step you need 2 reactions. So I will add in the Grignard, and then we'll do the work up with some of the acid or water. This will give you what? So this will give you the primary and the secondary alcohol. Right. Now I will go this way. So we know we have very, very few, quite a few choice, okay, to go from secondary alcohol into a ketone. Pretty much all those oxidizing agents you can memorize can oxidize your secondary alcohol into a ketone. Okay? Now let's make a list of them. Okay? First, any of the following can oxidize your secondary alcohol So what were our lists? We can use CrO3 in some of the acid, let's say in H2SO4. Sometimes I will simply write, maybe give you Na2Cr2O7 dichromate. In some of the acid, H2SO4. Okay, so those are all these. All those PCC or PDC. So even PCC and PDC, you're mild, oxidize your primary into aldehyde, but they still can oxidize your secondary into ketones. Then the last one, what about our sperm? Okay, any questions? Now let's study the reactions of aldehyde and ketones discussed in early chapters. reaction pretty much is, let's say this, in this section is reductions. So I'm going to say we reduce them into either alcohol or hydrocarbons. First, let's say we reduce them into all the way into hydrocarbons. You have the carbonyl in aldehyde and ketones, and we studied that in chapter 12. And we can reduce, we can totally get rid of that carbonyl, that double bond O, and simply become all those hydrocarbons. There's no oxygen anymore. Two ways to do that. One is a Imines reduction, the other one is a Wolff-Kishner reduction. Right. So you can see if you have this as a product that come from that reduction of a ketone, your ketone will initially work with this ketone. I think this is one of the questions, similar question on the exam. If you want to produce this one, directly by using the Friedel-Crafts alkylation, you cannot. If you take a benzene, and then plus, let's say this is isobutyl chloride like this, and you use your catalyst, the AlCl3, because this is called alkylation, and you hope you will produce this. You hope you will produce this. And then we say cannot. What you really produce, if you use these two reagents, what you really produce is this. Let me show you what you really produce. Right? You will have the carbon cation, and the carbon cation are rearranged. So instead of adding isobutyl group on the benzene, you actually adding a terbutyl. Now, if you really want to adding the isobutyl on it, you have to go 2 steps. You first produce this. You can produce this from benzene by adding this. By adding this acyl chloride, or you can use anhydride. So if you use this AlCl3 and this acyl chloride, then you will get this. Now this question is about the reduction. So when you have this, you can reduce into this. Now this question was on the exam. So I want you to give me 2 steps to prepare something like this. Okay? So you cannot use that step. You see, I will take a benzene, and I will take the isobutyl chloride, and I will produce this. But that's not having that much, maybe like only a few percent. So therefore, it's not the right approach. So what you do, you will take the benzene first to acetylation, then reduction. Now just remember the reduction, we have 2 ways to reduce that. We can use the so-called the zinc mercury amalgam in HCl, and that will do it. That will like get rid of this carbonyl and reduce into the hydrocarbons. See here, there's only carbon So other reducing method, if you want to get rid of your carbonyl, you change your C*O into CO2. That's the reducing process. You're using the Wolff-Kirchner reagent, which is a hydrogen and some base, and then you have the heating up this. So therefore, you will use some of those high boiling point solvent. Right? Now see if you can identify this process. Okay? On this reagent, we have a carbonyl and we have a double bond. If you use those reducing agents, it's selective. You will do nothing to the double bond. And you will produce this alkene. So carbonyl disappear. Those reaction review, right? Those reaction review. Now the next objective is reducing those aldehyde and ketone to alcohols. That's what we just studied in chapter 15, like in the cover chapter. Okay, now we'll review this 4 ways to reduce the aldehyde and ketones into alcohols. So first is adding H2 over the metal catalyst. The second is use NADH4. And the third is using lithium aluminum hydride. And then the fourth one is adding the Grignard reagent or the organolithium compound. So first, let's review. We have those carbonyl compound, aldehyde and ketones, and we're adding H2, and we will reduce the carbonyl into hydroxyl. Aldehyde change into primary alcohol, and ketone will change into secondary alcohol. So once you memorize the general equation, let's use it on the specific examples. If I take this para-methoxy benzaldehyde, and let me see, I use some of those agents. I will just use H2, okay, and use platinum, PT. What will this produce is your alcohol. You pretty much still have the same carbon frame, but this becomes the benzyl alcohol. Okay, now vice versa. If I give you the reagent, give you the product, I want you to identify how can you produce this product from the given reagent, according to what we just studied. You can use all the 4 methods, but here you will use adding H2, and this time we use palladium, PD. So then you will use some of the hydride reducing agent one of those hydride reducing agent NaBH4. NaBH4 is a liberal, mild reducing agent, but it works like in any those environment. It works when you have water or acetal, alcohols. It's mild reducing agent. It cannot reduce like acid. It will reduce it is very slow, pretty much not that much effective. Let's see, but it can reduce those aldehyde and ketones. So very similar as you adding the H2 over metal catalyst, reduce the aldehyde into primary alcohol, reducing the ketone into secondary alcohol. So one example we have here is M-nitrobenzoyl. And let's see what that will produce. If we adding this NaBH4 in C3OH methanol, right? So what will this produce? What will this reduce? This will reduce the aldehyde found in the group into an alcohol. You still have that M-nitro. Now let me see if we can move this. This is our product. You can move this way. I prepare those red notes with a different format. Move that. But anyhow, let's do it this way. So I have this reagent, and I wanted to identify what you can use to change into that product. So far we have two now. What's our first way to change that into our alcohol? Yeah, we can use H2 with this time we can use nickel, right? Nickel, platinum, palladium, or ruthenium. Or no, we also saw it the second way. Or use what? NaBH4. Remember that? NaBH4, let's say in the CH3CH2OH. Now this time let's say in ethanol. Because the carbon chain getting a little longer, probably you use ethanol will have a better solubility than use methanol. So number 3 is using the lithium aluminum hydride. Lithium aluminum hydride is similar as so this guy is similar as NaBH4, but is more powerful. It can reduce a lot of compound. Aldehyde and ketone you can reduce, but it's kind of tedious. You have to be very cautious. You have to use 2 steps. You first use the lithium aluminum hydride in those anhydrous environment. Use diethyl ether, and then use water to work out. All different ways to reduce. So what we can use here, if we have that aldehyde, Here was you can use Li8LH4 in diethyl ether. So this is diethyl ether. And second step, you add water in. Now the second example is I try to ask you if I have this product and I use first step Li8LH4 same solvent. If I want to use the same solvent, in that diethyl ether, then I will do H2O. So the question is, what is our reactant? Not that difficult to identify. You just identify where's the alcohol, then you will replace the alcohol that functional group by aldehyde or ketone. This is the ketone. I thought our alcohol is seen on this part. This alcohol is on the side of the carbon. Okay. So the last way to reduce the aldehyde ketone into alcohol, we just see like yesterday we do those quiz on the board. Either by adding those Grignard or organometallic. This we really already studied a few times, right? So this method it works good because not only you adding like more carbon, and it's also produce a very important intermediate is alcohol. Right? And you can add in some of those Grignard or organometallic. So let's say this. I have the reagent, have the product. Just want to identify. What shall we add? How can we change this ketone into that alcohol? You cannot simply use NABH4. Use NABH4, this will change into simply your cyclohexane. Right? So you have to think about convert this guy with that, you have some more carbon. So what you will add is you will add like your first step, right? You will add some of those you will add Grignard. So this will in the aprotic solvent, as in this diethyl ether. Then you add water. And that will produce our alcohol. Any questions? Now let's see what we see the chemical reaction in this chapter. In this chapter, we will study the reaction of aldehyde ketones. The typical reaction for the aldehyde ketone is a nucleophilic addition in this chapter. And then in chapter 19, you will see those carbonyl. Also can have those nucleophilic substitution. But for the aldehyde and ketone, mainly the nucleophilic addition. The general equation is you have this carbonyl, you have this X and Y, and your Y was the nucleophile, your X was the electrophile. So after addition, your electrophile will add on to that oxygen, and your nucleophile will add on to the carbon. So you break the carbon oxygen double bond. There are quite a few of this nucleophilic addition for the aldehyde and ketones. That's a very interesting section. The first one we'll see the so-called hydration. The hydration of aldehyde and ketones depends on the structure of aldehyde and ketones. For some aldehyde, the reaction rate is very, very quick, and your equilibrium constant is very large, which means you will produce a lot of those hydrates. Okay, so the general equation is you take aldehyde or ketone and you change the carbonyl into like the geminal diol. And this is for the hydrate. Depending on the structure, for the formaldehyde have a carbonyl and only 2 H. And we know H is not very good like electron donor. So this carbonyl carbon here in the formaldehyde have a lot of positive charge. And when you adding more and more those alkyls, if you replace one H by CH3, so that will stabilize your carbonyl carbon. Make the carbon here get a little less positive charge. In addition to that, you have this the CH3 vessel a little larger, so give a little more like a spherical hindrance. Your nucleophile has to come in to attack this carbon. If you have very small H, so there's pretty much no blocking. If you have a CH3, so that some of those space or room is taken by the CH3. So the hydration of aldehyde and ketone is actually change your carbonyl into 2 hydroxyl on the same carbon, and we call that geminal diol. And obviously, if you need the nucleophile attack the carbon near carbon, because carbonyl carbon is relatively positive, if you have something in your structure and make the carbonyl carbon more positive, then your nucleophilic addition reaction will happen easier, faster, and your equilibrium constant will be larger. That means you will produce a lot of those hydrates, geminal diol. This example is we replace those 6 H in the acetone by 6 fluorine. Fluorine is very electronegative. So this very electronegative fluorine will take electron away, take more electron away from the carbonyl carbon, make the carbonyl carbon more positive, so that your hydration has like the equilibrium constant is about 10 times, even 10 times larger than the formaldehyde. So this table compare, summarize those few aldehyde or ketones. The comparison, the relative rate, compare is with the acetaldehyde. And the pretty much 2 factors that will influence your reactivity of the carbonyl carbon. One is the electronic effect. The other one is the steric effect. And here I just show you the steric, compare the steric, and you can see the steric. The C3, the methyl is larger than the H, so therefore the rate of hydration going from left to right and decreases, and your equilibrium constant also decreases. This red arrow means decreases the rate of hydration and decreases of that equilibrium constant K. Right. So at least we know what can happen to the carbonyls if we have water and we can have acid catalyzed hydration or base catalyzed hydration. The hydration, that means you will change the carbonyl into geminal diols. And this neat-fin products or knockout drop is like the chloro with a common name for trichloroethanol, and trichloroethanol, which means you have this ethanol or acetaldehyde. Trichloro, that means you have 3 chlorine on this carbon, and then you want to write the formula for the hydrate of this compound, and then you know what is the hydrate of this compound. Just replace the carbonyl by 2 hydroxyl. Okay. Has the following hydrate. Okay. So the hydrate, you will have this Cl3C and then CH and OH and OH. So this is the so-called geminal diol. So we are going to see 2 mechanisms of hydration. One mechanism is hydration in base. The other one is hydration in acid. Right? So in base, you will have the hydroxide. Right? Hydroxide might come from sodium hydroxide or potassium hydroxide. And let's take a generic aldehyde or ketone. So we have this R and R prime. And we have 2 electron pair emitted on this oxygen. Okay. So the first step is your nucleophilic addition of hydroxide ion to the carbonyl carbon, or to the carbonyl group. The carbonyl group has C and O. Okay. O has relatively more negative. So the attack naturally will occur on the carbon, because carbon has more positive. So this step is reversible, is slow. Okay, now in the same time, you will push 1 pair of electron onto oxygen. Now the oxygen will have 3 pairs, negative, and then you have this R, and R prime R, and HO. Now let me erase those. So that's was from last batch. Okay, so that's pretty good. Any questions? Okay. Second step is if I tell you proton transfer from water to the intermediate formed in step 1. Right? So your intermediate formed in step 1 is HC and O and this 3 pair of electron, and then you have this R prime and R. Proton transfer from water. So you have water and H2O our product is a germinal diol. Then we recover our catalyst. Mechanism of hydration in acid. In acid, protonation of the carbonyl oxygen. So if we take again our generic ketones, so we will have this R and C, double bond O, and then R prime. Initially two long pair electron on the oxygen. Protonation, that means you adding a proton on some atom. This is the reversible fast step. You produce protonated aldehyde or ketone. And now this become plus. And at the same time, you produce the H2O. So the H3O plus becomes H2O. Okay? So a little bit more tedious than the base catalyze. The next step, you will take that intermediate. Now it has a positive charge on oxygen because it's lost one lone pair. This is a tag of water. This was a slow step. Once we have that, it's almost our product, almost like the germinal diol. You can separate one more proton on the water you just add on. Okay? So you have to take that off. I just rewrite our intermediate. Right? So you can use water to take off this proton. This is H3O plus. Okay, see if you can see all the 3 steps. You can see the last 2 steps, right? The first step, is protonation, right? You have the carbonyl and grab an H from those acid catalysts, try to use that protonated carbonyl. So now that carbon become more electrophilic. Okay? So therefore, this nucleophile can attack that carbon even easier. And you put the electron out onto that O, you produce this, almost our Gemini diagram. Right? As I said, when you have those structures, like have a kind of like H2O with a plus charge on O, you can take the H plus away by using another base. Okay? So here, the last step, you take the 1 proton away from here, okay, by this water. Then you will return like 2 electrons back onto this O. So that's the mechanism of hydration in acid. Any questions or comments? So the second reaction we will start in this chapter is a cyanohydrin formation. Okay? You will take some of the carbonyl and use HCN. HCN usually is not a good nucleophile because that's a weak acid. So you don't have too much of those CN1 negative. CN1 negative is really the one that's acting as a nucleophile and onto your carbonyl. So what we do, usually we use some of the acid, you have this HCN, but you add some of the salt of HCN. You can produce the salt of those amines by taking HCN reacting with sodium, for example, sodium hydroxide or potassium hydroxide. Those are very similar acid-base reactions. Now let's see some of those examples. Okay. So if I have this carbon, benzaldehyde, some benzaldehyde, and you have this, let's say you have 3, you cannot use M and P or O, so you have 2,4 dichlorobenzaldehyde, right? And so this, you can treat this with NaCN. The solvent is diethyl ether and also H2O, so that's our solvent. So this was our first step. The second step, we are adding those HCl. Okay, so what is the product? You will not do anything to that 2Cl. So you have Cl here and Cl here. And then this H is still here, OH, OH. Oh, not OH, OH. OH is seen. Questions? Similarly, if I give you this product, what should we use? That's good. What do you use to get that product? All right, reaction kind of like backward way. Okay. We first need some of those aldehyde or ketone. Okay. So you have these 2. The hydroxyl and cyanide on the same carbon, that means that carbon initially was a carbonyl. Okay. So your reactant will be this ketone, acetone. What you use NaCN and H2O. And then you add H2SO4 or HCl like in last example. And you have to control how much acid you add. If you add too much acid there, you will lose your nuclear fire. So pretty much initially you just take some of those NaCN in water, and once this happens, that means you are adding this CN on this side, you will produce the O1 negative. That O1 negative will take the proton from water or from acid. Now let's see the mechanism. Okay? And you will see the mechanism. So first step is to negatively charge the carbon of the cyanide ion in the nucleophile. And bound to the carbon of the aldehyde or the ketone. Okay. So now let's take this cyanide ion and write out the loose structure. Okay. So this carbon have a -1 forward charge, and that will be the nucleophilic site, nucleophile, and sometimes you will have the few atoms. And really, which atom has more negative charge than the atom that will attack those electrophiles. I don't have space on the top, so therefore I will write my second R just here. Okay. Now the nucleophilic attack, which means you are taking the negative charge and attack the carbon. Carbon cannot have a 5 chemical bond. When you see those arrows, that means you possibly will produce a chemical bond. Right? If you add a chemical bond, and you have to make sure what atom you add, you cannot have a 5 chemical bond on carbon. Now step 2 is this, this is the we call that carboxide ion. Now let's rewrite it here. So this is going to abstract like a proton from water or from something like this HCN. Well, you want to abstract it from HCN, there's some reason. Because if you take the proton away from the HCN, you will produce your reagent you need in your first step. Right? So now plus the CN negative charge. And this is the guy you produce here. In the second step, you can use in your first step. Right, any questions? Okay. Now the very tedious writing, the next one. is the formation of acetal ketone, acetal ketones, or hemiacetal, hemiketones. These look like this. So you start with some carbonyl, aldehyde or ketone. You add one alcohol, very similar as you adding a water, and you produce this guy. Look at this guy. This have a carbon, have a OH, and have a ether. Right? Then you add another alcohol. Then you will replace that hydroxyl alcohol, so that will go out as water, and then you produce this kind of diether on the same carbon. Okay? So we call those acetal. Why that is interesting? Couple reasons. One reason is a lot of those hydrocarbons, sugars, and they naturally exist as a hemiacetal. Glucose, right? Fructose, or sucrose, they all exist as a hemiacetal. Cyclic structure, hemiacetal. The second reason is from this figure you can see sometimes you can use acetal as a protecting group. In some reactions, you will have two functional groups potentially can have the same reaction, but you can selectively protecting one group and then let the other group have that reaction. So then after that reaction finish, you can remove the protecting group, then you will have the process. So let's see the example. If you, I think first you will memorize what we do. If I give you aldehyde, give you two alcohol with some of the acid catalyst, that means you will produce all the way to the acetal. And what you produce is change the carbon into something like this. Depending on the alcohol you use, the alcohol you use is acetal. So therefore, you will have two carbon here and two carbon here. And spill water out. So typically, it's difficult to isolate the hemiacetal. This is the hemiacetal. For this example, you will see this. You have the acid catalyst. You will go all the way to the acetal. You did not stop in the middle here. You take this part away. You have H. So that will be the hemiacetal. Right? You do both of these replaced by this attending the alkoxide on the carbon. But if you are, for some of the molecules, as mentioned, glucose, sucrose, they can produce the cyclic intramolecular hemiacetal. And then that is more stable than the acetal. You can still change those hemiacetal of glucose and sucrose into the acetal we will study in chapter 23. But you have to add in some of the other reagents. Now, because usually you will not see the hemiacetal, but you still can see the hemiacetal for those carbohydrates, sugars, right? So therefore, we will study two mechanisms to produce the hemiacetal. One mechanism is the base catalyzed. The other mechanism is acid catalyzed. To produce all the way to the acetal, you must use the acid catalyzed. Right? So if you want to go all the way to the acetal, you have to use acid as a catalyst. If you want to start in the middle of the hemiacetal, you can either use acid or base. Usually cannot stop that easy as the middle of hemiacetal. But for those intramolecular, like those glucose sucrose, you can start in the middle. So we'll study both ways to produce hemiacetal. Then we'll use the acid catalyst to go all the way to the acetal. It's, the overall process to produce acetal is a very lengthy process. And we'll see this. If you think about this whole process going from aldehyde and ketone with the acid catalyst all the way from your ketone all the way to the acetal, you will have like you will have a 7-step. This 7-step we divide the 7-step into 2 stages. Stage 1 it produces the hemiacetal, and stage 2 is like the hemiacetal change into the acetal. So let's first see the first stage. The first stage, which means you will produce the hemiacetal. And let's first study the base catalyze. So according to what we said here, the first step in the base catalyze the formation of hemiacetal, which you will take an aldehyde or ketone with alcohol, is take a proton weight from the alcohol to give the alkoxide. So let's see that. So let's see, we use a generic formula for our base, just B is not an element, not a boron. Okay? So this is not a boron. So B is standing for base. So the B is for base. You might use sodium hydroxide as base, or you might use sodium imine, what we studied in Chapter 9. Your alcohol has the OH, and let's use our generic formula OHR or HAR. So this will come here, take the proton, and then put your electron back on the oxygen. This reaction is reversible and fast, because usually they said the acid-base reaction happens very quick. And you produce the pH and alkoxide. -1 charge. So this alkoxide will be our nucleophile. And our electrophile will be the carbonyl carbon. Now this time, we will simply use acetone as one example. Acetone has 2 methyl and 1 carbonyl. Now our alkoxide is produced from step 1 and will now have a 3 lone pair on this oxygen, carry a -1 charge. Okay. So this will be our nucleophile, and our carbonyl carbon will be our electrophile, and the chemical reaction will, a bond will produce between your nucleophile and electrophile. Now let's emphasize, so this is the nucleophile, okay, and your electrophile is the carbonyl carbon. So you will see this become, the oxygen become -1 charge. -1 charge. At the same time, you produce this, you adding on this aurora. Now you think about like what you want to produce, so that will make you, it will help you to get to the figure out the mechanism, right? So what you want to produce is a hemiacetal. Hemiacetal, which means have the OR on the carbon, and also have the OH on the carbon. So now, so far you have the OR on the carbon, and the other side is the oxygen negative. So obviously you want to change that into OH. Everything is take this intermediate. So we have this OR here, and then we have this oxygen negative one charge. And you can take some of the proton from alcohol or from water. Water can be the solvent. The alcohol we use is HOR. And this is negative one charge, right? So that is what happens. So this proton, this electron can take this proton away, and then you will put back two pair of electrons, and one more pair of electron onto that oxygen, and you produce. Produce this, you still have this OR, now you produce this OH. This is super hemiacetal. Remember this mechanism overall have 7 steps. The first 3 steps, we call it, when we produce this hemiacetal, this is your first stage. We divide the 7th step into 2 stages. So this will be the end of your first stage. For some molecular, your hemiacetal is stable. Now let's again we'll try this 3 steps to produce the hemiacetal. This time we will start with the acid base, acid catalyze. Right? So according to what I write here, when you want to produce the hemiacetal with the acid and the catalyst, your first step is a protonation of carbonyl oxygen. Now again, we'll use our acetone as the example. So acetone has 2 long pair of electrons on the oxygen. Acid catalyzed, that means we have a lot of acid. Now this time let's use H3O plus as our acid. Well, H3O plus you probably write spell out the H3O plus real better. So that means you have H and H, and here plus. Okay, so you did that like already quite a few times. Protonation really means adding proton. Right? Now this time your protonation will happen on this oxygen. So you will take some electron from the oxygen and try to make a bond between your oxygen and the H. So then this will push this bonding pair of electron onto the oxygen. Okay, so what we produce second step is you will do a nucleophilic addition Now this only have one lone pair, have a H on it. Okay. And your alcohol, as we will take our alcohol as O, H, and R, like that. So this electron from the oxygen acting as a nucleophile attack the carbonyl carbide, and your electron must push back because you cannot have 5 bond on the carbide. Now the alcohol oxygen has a positive charge. So therefore, there will be the step 3. You need to deprotonate the alcohol oxygen I'm going to rearrange this structure here. It was different than what you saw at the beginning when it was produced. Okay. But these two cells are basically the same, right? So you have that OH and OH, and our aldehyde ketone initially was acetal. We have 2 methyl. Now this part here, I just flip this R because you are ready to take this H away. Once you take this H away, you produce the hemiacetal. Right? So because we use H3O plus as our acid, and we are going to use H2O as our base. So that's plus H2O as our base, and then our H2O can take the electron away, and these 2 electrons will get back onto the oxygen. So therefore, you produce the hemiacetal. So this is OH, and then this is OR. Again, this is the end of first stage. We have 2 stages to produce acetal. Altogether 7 steps. For the first 3 steps, you can either use base as the catalyst or acid as the catalyst. Now the next 4 step, you must use the acid catalyst. So now what do you do? If you use base catalyst to produce the hemiacetal, you're going to change that into acid. You can do that. You can just add in more acid and change it into acetic for the environment. Okay? If you start with your hemiacetal with acid, you just continue and adding more alcohol, you produce the acid. Right. Now let's take our, I think that one is relatively simple. I will take that hemiacetal we produced from the first step, which comes from the acetone. And let's write it here. So we have the 2 methyl, and let's see, we have that O and H there, and let's put that H on that side, and we are ready to take 1 more proton, adding 1 more proton onto that oxygen. Right? Because this will give you the name on the quick. I will say that this step 4 is the protonation of the hydroxyl oxygen. You know which is the hydroxyl oxygen, right? So this is a kind of your ether oxygen. This is a hydroxyl oxygen. Protonation, that means you adding a proton onto this oxygen, not on this. Not on this. While reality, both can happen. Okay? But if you have this happen, you will revert back to the first step. Therefore, in all those steps we see we have those reversal. Okay? And once you protonate this, your reaction going forward, so therefore those reactions will have the percent yield. Or the reaction will be slow going forward. Because you always have those possibility of reverse. Overall, if it's one step, okay, all those are equilibrium, if one step will draw your product or take the product away, that means they are going forward very easy. So now let's again use our H3O plus as our acid. So protonate, that means you take one proton away from this H3O plus, and this will bounce back, and you will see you will produce a protonated so there's a 2H on this row. Now because this oxygen now has a 3 chemical bond, so therefore it has a positive 1 charge. And you will produce at the same time the water. So then guess what? So next step, you have this 2 lone pair here on this oxygen. I will redraw it here. This O here have 2 pairs. And this H, and that one I don't have to write that out. I can simply write HOH2. Only have 1 pair, so that O has a positive charge. Now what I have here is this electron come in, produce double bond, then that will kick out that H2O as a leaving group like that. It's kind of like a E1 elimination. This looks ugly than that. Ready? Now this has a positive charge. I have only 1 pair now. I want to keep the similar structure as what we have here. So you pretty much, you don't change anything out of the frame. Just move a pair here, but it's double bond, so therefore we have double bond here. Now you have a 4 bond, so therefore the initial bond between the O and the carbon break. That means your water left. So therefore plus H2O. Now this guy can resonance. Okay? You can move this electron back, then you have a positive charge here. Or initially you don't think about this going there, just think about that just go away by itself, and then you have a positive charge on this carbon. That's a carbon cation. And that was get ready for the next step. So if you want to write out this resonance, let me put the word somewhere else. I will write this resonance, you will like have more space. Okay? So let's see, I will write plus H2 here. I will have more space to write the so-called resonance. Right? So you already know the resonance process many times. I think most of you did pretty good on the last exam. I give you some of those carbon cation and you want to produce other resonance structures. So what you do, you will take one pair of electrons here and put it back. Okay? And you will produce this resonance. Now this has two pairs. Now this has a positive charge. Then the next step will be easy, because the next step is the nucleophilic addition of acetal to the oxygen stabilized carbon cation. You can take either this resonance structure as your next step, and I think this is a measure because everyone has oxide. Even though for the purpose of simplicity, some books like to use that one, because that one you will have the positive charge. Then the alcohol can say that attack that positive charge make more sense. But depends on the book of the author. Okay? So I will probably just keep using our measure. So this is a major contributor, and this is a minor contributor. Okay? Even though make sense in terms of make sense or not, you probably will use the minor. Then you have to think, okay, I use the minor, and even though minor not that much, but if you use a little bit, and your measure will change the minor. Use a little more, then more measure will change the minor. So all the measure will finally change the minor. So now let's see, we'll take another alcohol will write up like this. So we use this as our alcohol. So almost there, right? The second step is very long, and what you see is this electron come here, attack this carbon. Okay, don't forget you write a positive charge here. And then this one electron will come back, will come out from the double bond and get back onto this oxygen. Now we have this OR, pretty good, right? Now you will have this O, and there's an H bonding to there that just simply comes from the alcohol. Now because this oxygen right now has 3 chemical bonds, so therefore it has a positive 1 charge. Yeah, so almost there. You see your acetal, which means has a carbon bonding to 2 of those OR. Right? Now you have one OR, the other one is OR H plus. So what you need to get a OR is simply take the H plus away. And then they will tell you proton transfer. Right? So let's take that. So let's take this. So this is the OR here, and you have O. And probably I will write the opposite because I need to take the H away. So I will write H here. Excuse me for that. Okay. So this is H, and this is R, and you still have 1 pair, but this is plus. Does that make sense? Okay. So this is almost our acetal. What is acetal? Acetal is those kind of compound, have a carbon, and have 2 OR. Right? So you have OR here, and here almost OR. What you need to do is simply take the H away. What we call that is deprotonation. And you can simply take some of those, for example, water, or some other alcohol. Yeah, so we'll see this electron come in. Then see this electron, you can change the pen, make sure you can see where this electron from the bond between O and H go. It will go from all the way from here and going back onto the O. So what's our final product? Over here and over here. This has a name, acetal. Okay, let's take a break. Take like a 5-minute break. Usually that's difficult to happen. So the hemiacetals, it's difficult to stop.
Okay, so the technique is once you put it in, it's like you can put the forms of that.
Even though you put one equivalent, however you will use the one equivalent converting half of that aldehyde ketones into the acetals.
Okay, and then they only protect at aldehyde or the
Protecting?
yeah.
Yeah, protecting, but I want to say, once you produce those acetals, those products are all reversible.
Yeah.
So it's acetaldehyde. So once you
But it'll protect it from the other reactions.
some other reaction, they don't use acid or base, and you can just still have the acetal in the group. Another group is down here, maybe a carbonyl, right? Maybe a carbonyl, maybe some other. Then you can let's say you have another carbonyl here, maybe aldehyde, maybe a triple bond, another one. Okay? So then you want to use a triple bond as a network by use lithium aluminum hydride or adding H2 and with metals.
Yeah, it won't reduce these because
You will not reduce it, but if you don't protect this. And this need to come from the acetal, from the carbonyl.
so you don't want to that will reduce people triple bond.
Right. You probably can also selectively protecting like one carbonyl, maybe a ketone or aldehyde. The ketone and aldehyde has different reactivity towards